Hello everyone, welcome to my channel oneconceptelectrical. This is one of the DC machine question. Let's solve this question. Given it is in 230 volts means the terminal voltage of 230 volts and running at a speed of 250 rpm and it is drawing a load current of 100 amps. Given it is a separately excited DC motor. Has an armature resistance of 0.5 ohm. The motor is connected to 230 volts. The motor is connected to 230 volts DC supply and rated DC voltage is applied to field winding. Means they are given the rated voltage applied to field winding means the field winding is kept constant. Given it is driving a load whose torque speed characteristics is given by TL equal to 500 minus 10 omega. Means the separately excited motor is driving a load whose characteristics as follows by TL equal to 500 minus 10 omega, where omega is rotational speed in radian per second and TL is in load torque. In this question, they are asking to find steady state speed at which motor will drive the load. They are asking to find the steady state speed along with armature current drawn from the supply. Before solving the question, let's summarize the data here. Given it is in DC separately excited DC motor, given terminal voltage at 230 volts, under rated condition it is drawing a current of 100 amps and armature resistance of 0.5 ohm. Along the given, the DC voltage applied to field winding means flux is kept constant. After these conditions, they are connected to some load whose torque speed characteristics is TL equal to 500 minus 10 omega. Before solving the question, let's try to find out at rated load condition. In rated load condition, they are already given motor is drawing a current of 100 amps. We already know the back EMF EB equal to Vt minus IA. IA is given 100 amps, armature resistance of 0.5 ohm. By this I can able to find the back EMF. Back EMF EB equal to Vt minus IA Ra. Then the back EMF is 180 volts at speed of 250 rpm. We already know EB equal to K into 5 into omega. We already decided flux is kept constant. Then K5 will be constant. By substituting omega equal to 2 pi ns by 60, I found K5 equal to 6.87 volt per radian second. Now, we go for condition where the motor is driving a load whose characteristics is TL equal to 500 minus 10 omega. Under this condition, let's suppose the motor is drawing a current of IA1. I am assuming the motor is drawing a current of IA1 from supply. Under this condition, the back EMF EB equal to Vt minus IA1 into Ra. Vt supply voltage is kept constant, means Vt will be 230 volts. IA1 we don't know. Armature resistance is 0.5 ohm. By this, EB equal to 230 minus 0.5 IA1. We already know K5 is constant, means under any load K5 will be constant. That's why from the previous case I am taking K5 equal to 6.87. We already know EB equal to K into 5 into omega. We substitute K5 value here. K5 is 6.87 into omega. K5 value is 6.87. By multiplying with omega, we get 6.87 to omega. I am comparing with EB. Means we already know EB equal to K5 omega. EB equal to 6.87 omega. From this equation, I am comparing with 230 minus 0.5 IA1 equal to 6.87 omega. By this I got an expression like this. I named this expression as A. Now the condition they given, the motor is driving a load torque. The load torque expression is TL equal to 500 minus 10 omega. We already know under steady state condition, electromagnetic torque will balance load torque. By using this expression, we know electromagnetic torque T equal to K into 5 into IA1 and TL, load torque equal to 500 minus 10 omega. I am equating these both expressions. We already know K5 equal to 6.87. By substituting K5 in this expression, I am got 6.87 IA1 equal to 500 minus 10 omega. I am naming this equation as B. Previously we got equation A. By solving equation A and B, I can able to find what is IA1. By solving these two expressions means there is only two variables, one is an IA1, other one is an omega. By solving this expression, I can able to find IA1 and omega. By solving these above expressions, I can able to find omega equal to 3.31.5 radian per second. Means when motor driving a load torque TL, its speed will be 31.5 radian per second. In order to find current, substitute this omega in above expression, either A or B or C. In the above expressions, I can able to find armature current is 27.19 amps. We already know omega equal to 2 pi ns by 60. If you want to find the speed in RPM, by substituting 31.5 equal to 2 pi ns by 60, by calculating I got ns equal to 300.75 RPM. Let's summarize the data here. Given it is a DC separately excited motor. Under rated condition, its speed is around 250 RPM. Now it is driving a load torque whose expression is 500 minus 10 omega. Let's suppose this DC separately excited motor driving this load torque, its speed will become 300.75 RPM and it starts drawing an armature current of 27.19 amps. This is a very good question. In order to solve this sort of questions, please subscribe to my channel.